Welcome back to the conclusion of section 5.4, more factoring of polynomials. This is for our polynomial unit, unit 2, chapter 5. Yesterday we discussed factoring a monomial and sum and difference of cubes patterns. Today we're going to pick up on these targets for the lesson. Hopefully at the end of the lesson you'll be able to factor a polynomial completely by grouping and using quadratic form, so two methods in one target there, and you'll be able to solve polynomial equations by factoring. So two goals here today. Write these down and have them ready to show me tomorrow in class. Okay, factoring by grouping. Factoring by grouping is a method we're going to use when we have four terms in a polynomial. So 4 terms in a polynomial, bigger than a trinomial, obviously. That's when you think factoring by grouping. You always, when we start any factoring method, hopefully we've kind of discovered this, or this is in the back of our brain, but we should always start by looking for a GCF to factor out, or factoring out a monomial term, like we did yesterday. Let's look at this one. 2 and 7, prime numbers. When you see prime coefficients or constant in the problem, you know that there's not going to be a GCF other than 1. Prime numbers are only divisible by themselves in 1, unless we have the same prime number, but in this case 2 and 7 are different, so we know there's no constant we can factor out, no number term. If you look at the variables, k is in the first 3 terms, but not in the last term, so there's no common variable to factor out either. So there is no GCF other than 1 that we can factor out. So the monomial, you just want to think about that first. It's going to make your life a lot easier if you factor out monomials before you get started. So let's factor by grouping. This is what you do. You put it in standard form, and then we group them. So we're going to take the first 2 terms, 2k cubed minus 7k squared. We're going to put them in parentheses. And then minus 8k plus 28 in parentheses. Always put a plus sign between the 2 sets of terms. It's going to make your life a lot easier. That minus sign that's in front of negative 8 goes with the 8k. So you can't leave a minus sign out there at positive 8k, it won't work. So if the third term is negative, you take it inside the parentheses, that negative term, and put a plus sign between the 2 parentheses. So here's the grouping part. Now here comes the factoring part. You're going to look for a GCF for the first set of parentheses, and then you will look for a GCF in the second set of parentheses. So let's look at the 2k cubed minus 7k squared. Ask yourself, is there something that divides out of 2k cubed and 7k squared? We already established that we don't have any common terms to factor out. So as far as common factors as far as the 2 and the 7 are concerned, but there is a common factor now if we look at just the k's. We have a k squared and a k cubed. K squared is the smaller of the 2 powers, so that's all we can divide out of the 2 terms. So we end up with k squared times, well, k cubed divided by k squared would be just k, so 2k. K squared divided by k squared, they cancel out, or we k to the 0, which is 1. 1 times negative 7, it's just negative 7. Now we have to do the same thing over here. Negative 8k plus 28k. If we look at this, what will factor out of negative 8 and 28? We don't have to worry about the variable because one has a k, one term, and one term does not have a k. So what will divide negative 8 and 28 evenly? Well, negative 4 or positive 4 will both divide it evenly. Which one do we want to factor out? Positive 4 or negative 4? Well, let's think about it. If I divide this just by 4, we end up with 4 on the outside, negative 2k, and positive 7. Here's the thing when you factor by grouping. When you get done, you know you'll have done it correctly if the same exact terms are in the left-hand parenthesis and the right-hand parenthesis. Do we have the same exact terms in each parenthesis? We do not. very close. Positive 2k and negative 2k, negative 7, positive 7. Each term is the opposite of each one. So I go back and I look at this. Should I have just factored out 4 or a negative 4? And so now we should be saying that it should have been a negative 4 that we divide everything by, which is going to change our signs here. It's going to change this to a positive 2k and this to a negative 7. Now we have the same exact terms inside the parentheses. We have negative or 2k minus 7 and 2k minus 7. We know we're on the right track. So, and from this point on, what do we do next? Well, from this point, let me so you can see the whole thing. From this point, we have to regroup them, so to speak. So we put them into two separate groups here. That's the first grouping part. We factored a monomial out of each term, and now we're going to regroup the terms. So we take these values that are outside the parentheses, negative 4 and k squared, and they're going to be my first group, k squared plus a negative 4 or k squared minus 4. Then this common term here, 2k minus 7, that's my second grouping. And you're saying to yourself, why is it 2k minus 7 squared? There's two of them. Well, if you put 2k minus 7 squared and you multiply it back out, you're not going to get what you started with. And really what we're doing here is we're reversing FOIL, or reversing the box method. If I were to FOIL this out, I would do k squared times 2k and k squared times negative 7. That's what this step is right here. And if I were to FOIL this out, I have negative 4 times 2k and negative 4 times negative 7. That's this step right here. So we're reversing FOIL. So the moral of the story is, even though it looks like it should be, you see 2k minus 7s, it's not 2k minus 7 squared. We're reversing FOIL, or we're doing this factoring and regrouping it. If you put 2k minus 7 squared, it's going to be wrong. So multiply it out, do the box, do the FOIL, test it. This is the factorization of 2k cubed minus 7k squared minus 8k plus 28. The only thing left to do, if you didn't do it at the beginning, is see, is there a monomial that we can now factor out of these terms? But there shouldn't be any more because you've done that already. So I always do it at the end just to make sure that I did everything correct. But you can see there's nothing that can factor out of either of these terms, either of these factors, so we are all set with this one. So that is factoring by grouping. Factoring polynomials in quadratic form. That means we're going to factor polynomials that are not quadratics, but kind of have the quadratic look or feel to them. For instance, 3t to the 4th plus 54t squared plus 51. It's a trinomial. So let's start out, when we look at this, first things first, can we factor any monomial terms out before we get to the quadratic part? That's quadratic or not. 3 is our smallest term, right? 3 is our smallest coefficient. So what are the factors of 3? 1 and 3. Does 3 divide 54? It does. Does 3 divide 51? It does. Try it on your calculator. We can divide these terms all by 3. So we end up with 3 times t to the 4th plus 54 divided by 3 is 18. And the t squared, don't forget about that. 51 divided by 3, that's 17. Oops, that plus negative 17. Pen drag there. Plus 17. So we factor out a monomial. Can we factor out what's inside? It's not a quadratic, but it has a quadratic look. And what I mean by that is, you look at the first power and the middle power, and then the last term is a constant, right? But the middle power is half as big as the biggest power. So squared is half the size of 4. That tells me this might be able to be factored in quadratic form. So if I had t to the 6th and t to the 3rd in the middle, t to the 8th, t to the 4th, t to the 10th, t to the 5th, that would be quadratic, possibly, anyways, model. So how do we factor quadratics? We're going to pretend, remember, pretend it's a quadratic. So for pretending it's a quadratic, it's bottoms up. A times C, rather, what adds to make, or sums to make B. My A and my C are 1 and 17, so 17, and my B value is just 18. So what numbers will multiply to make 17 and add to make 18? Well, 1 times 17 is 17, and 1 plus 17 is 18. That combination appears to work, so we'll factor it using those numbers. So 3, remember we factor trinomial, ends up into 2 binomials. I'm just going to put t, and we'll talk about what t power we're going to have there. I know that we're going to have, they're both positive signs here, so plus 17, plus 1, or plus 1, plus 17, either way. What power of t do we need? Well, these t's have to multiply together to make t to the 4th power. T times t is t squared. What multiplies to make t to the 4th power? Well, 3 and 1 would, but when we FOIL that out, obviously we're not going to get a t squared term. So both of these terms need to be t squared. And so now we have factored it into 2 binomials. The only thing left, and sometimes this happens, is you look for a difference of squares pattern, or some difference of cubes pattern if that's the case. In this case, these are quadratics, they're squared binomials, t squared and t squared. We look for a difference of perfect squares. The only one that has a chance is this t squared and 1, but it's a positive sign, so it's not a difference of squares. So here is the complete factored form of 3t to the 4th plus 54t squared plus 51. I would check it by FOILing it back together. First of all, I'd probably do it in stages. 3 times t to the 4th times 18t squared plus 17. I would, in other words, multiply this back through, make sure I got this answer up above. And if that checks out, then I would make sure, just check to make sure to FOIL this t squared plus 17 times t squared plus 1 to see if you get the t to the 4th plus 18t plus 17. Or you can FOIL it and then distribute and make sure you get the whole thing, however you want to do it. But I would always double check. Whenever you're doing a factoring problem, you can always check by FOILing or using the table method. So do so, especially tests and quizzes. This example number 2 is a little bit different. We're saying quadratic form. What quadratic form do we have here? Well, first of all, always look for monomial terms. Is there a monomial term we can factor out of 10s to the 4th minus 10? I hope that we can see that 10 divides both of these terms. So 10 times s to the 4th minus 1. So s to the 4th minus 1, that doesn't look like a trinomial. We talked about it in the last one, I mentioned it anyways, difference of squares pattern. Is s to the 4th a perfect square? Well, s to the 4th can be s squared times s squared, can it? And negative 1 can be 1 times 1. So, excuse me, s to the 4th and 1 are perfect squares. We have a subtraction sign, so we have difference of squares here. So, s to the 4th is just s times s. So, there we go. S squared, in the first part of each parenthesis, 1 plus 1 and a minus 1 in each parenthesis. So there's the difference of squares. If you don't believe me, FOIL it back through. Do the box method. Double check it. We're going to get s to the 4th minus 1. Are we done? Well, we have to see if can we factor anything else. S squared plus 1, that's not a difference of squares pattern. That's not going to work. There's no monomials to factor out. But s squared minus 1, is that a difference of squares? Well, believe it or not, it is. S times s is s squared. And we already know 1 times 1 is 1. So, s squared plus 1, nothing to do with that. But s squared minus 1 is s minus 1, s plus 1. And this is now our complete factorization of 10s to the 4th minus 10. So really, remember this. You always have to, for polynomials, especially the past quadratics, there rarely is going to be a factorization problem that is just one step. They're usually multiple steps, and usually 2, 3, 4 steps. So just factoring a monomial is not going to always do it. Just doing difference of squares once isn't always going to do it. You might use difference of squares over and over again, or factoring it like a trinomial as if it were quadratic. So keep that in mind. Okay, so we accomplished our first two targets. And now we're looking at our third target, which is solving by factoring. So let's look at example one. Example one here, we have 4x to the fifth minus 40x to the third plus 36x. What would we do here? Well, to solve it by factoring, you would try and get it completely factored and solve for each factor, just like we did in Chapter 4, Unit 1. So let's look at the problem. We have 4, 40, and 36. 4 is my smallest coefficient. Is there a number that divides 4, 40, and 36? Well, 1, 2, and 4 divides 4. Will 4 divide 40? Yes. Will 4 divide 36? Yes. So I can factor out a 4. And then we look at this. Is there a number that divides, or excuse me, a common variable in all three? X to the third, and x to the fifth. The smallest power of x is x to the first. So I can divide each of these by x. So put that together, we can factor out a 4x out of each of these terms. That leaves me with x to the fourth minus 10x squared plus 9. So can I factor further? This up a little bit here. Can I factor x to the fourth minus 10x squared plus 9? Can I do that with difference of squares? Nope, that's not difference of squares. But we might be able to use bottoms up. It's a trinomial. So my a times c is 1 times 9, which is 9. My b value is negative 10. What multiplies to make positive 9 and adds to make negative 10? Give you a chance to think about it. Pause it, and then press play when you're ready. Hopefully you saw that both factors have to be negative, because we're adding to make a negative term and multiplying to make positive. Negative 1 times negative 9 is positive 9, and negative 1 plus negative 9 is negative 10. That's our winning combination. So we end up with 4x times x squared, right, because it's x to the fourth, minus 1, excuse me, and x squared minus 9 equals 0. Can we factor any further? Now, you're solving this, and if you solve by square roots, you wouldn't have to go any further if you didn't want to. You could do x squared minus 1 equals 0, x squared minus 9 equals 0. Let's just practice our factoring here. Can we factor x squared minus 1? Is it a difference of squares pattern? Indeed it is, right? X times x is x squared, 1 times 1 is 1, so x minus 1, x plus 1. X squared minus 9, x times x is x squared, 3 times 3 is 9, so x plus 3, x minus 3 equals 0. And so now we're going to solve. Now that's the complete factorization. Remember, it said solve. Or it may say something like find the zeros. Remember, that means the same thing. So you take 4x, set it equal to 0. You take x minus 1, set it equal to 0. You take x plus 1, set it equal to 0. You take x plus 3, set it equal to 0. And finally, you take x minus 3 and set it equal to 0. When we solve each of these equations, we see that we get x equals 0. We get x equals 1. We get x equals, equal to 0 here. X equals negative 1. We get x equals negative 3. And we get x equals positive 3. Those are the zeros. Those are our solutions for this problem. A way to check this would be to graph it. If you have a graphing calculator at home, this would be a good way to check it, a fast way to check it. I'm going to put in 40x to the fifth. Excuse me, 4x to the fifth. Not 40. 4x to the fifth, here's a 40 result, completely crazy, minus 40x to the third, plus 36x, equals 0. Remember, put 0 in for line 2. And so you can graph it, and we can see if we can tell where it crosses the x-axis. And it looks like it crosses at negative 1, 2, 3. That was one of our solutions. Looks like it crosses at negative 1. Looks like it crosses at 0, 1, and positive 3. So from a graph, we can tell it's not always that easy. So we can, there's two ways we can look at it. We can go to the table. We can go to our inputs. And we can see at negative 3, we have a 0. At negative 1, we have 0 as an output. At 0, we have 0 as an output. At 1, we have 0 as an output. And at positive 3, we also have a 0. So that's one way to check. From the graph, we can go to second trace and just plug in our values. I'm not going to plug in all, but let's plug in positive 1. Y is 0. So we could go through and try all of them that way. We can also find the zeros if we, since we put y equals 0 in there into our equation, we can go to intersect and we can find the zeros that way. And all you have to do is hit enter 3 times and it gives us a 0. And you want to do the next one or a different 0, hit enter and then arrow over until we get close to another point. Oops, I'm sorry, I did the 0 function. Let's try that again. I'm going to intersect. We can do it by 0 as well, but intersect I think is easier. Hit enter, and then we're close to this point. Enter again, it gives you 3, 0. So you can do that over and over again. So those are ways to check your answers to see if it makes sense. The graph and factoring methods should point to the same answer. If they don't, you did something wrong. Okay? So I think we successfully covered our targets for today. We're going to practice more tomorrow, but you should be able to factor in by grouping and factoring using quadratic form, both trinomial form or difference of squares. And we solve polynomial equations by factoring, using these methods to actually find the 0th number. Always check your work, whether it's by foiling, whether it's by the table, and when you're just doing the factoring, and then always solve your solving equations by graphing them in the graphing calculator and using one of the methods we just mentioned. Have your notes ready for tomorrow. We will be doing more practice. Have a good evening. See you tomorrow.